This video is going to give an overview of working with quadratic functions. So first, when we put a quadratic function, which is something with an x squared, in the following form, f of x equals a x minus h squared plus k, we're putting it in what's known as standard or vertex form. This is called vertex form because we can use our graphing transformations, the ideas from an earlier video, to understand where this graph is on our coordinate system and what it looks like. For example, if we start with the parent function, y equals x squared, that's our basic parabola. This minus h is going to shift the graph right h units, if h is positive. The plus k will shift the graph up k units, if k is positive. So my basic parent function, y equals x squared, would look like this yellow parabola. If I move it over to the right h units, up k units, that shifts the graph's location to what I've drawn in green. And so the vertex of our quadratic is this bending point. In this picture, that would be the minimum point of the graph. When we make those shifts, the vertex is now located at the point hk. So this is known as vertex form because we can see where the vertex is in the equation. It's going to be at h, k. Now the other number, this a, is going to be your coefficient of your x squared. If that number is positive, your graph is going to open up, just like I have shown in my picture. But if that number is negative, if a is negative, that means we'll have a reflection and our graph is going to open down. All right, so let's take a look at some specific examples. Let's see if we can find the vertex, axis of symmetry, domain, range, and graph. And we're given the function f of x equals x minus 2 squared plus 1. So I'm actually going to do my graph first. Here's my parent function, y equals x squared. This minus 2 is inside the parentheses. That's going to shift the graph to the right 2. The plus 1 is an output transformation. That's going to shift the graph up 1. So I take my parabola, move it to the right 2, up 1. Based on that, I can see that my vertex is located at the point 2, 1. And I can actually see that by looking at the equation. This 2 right here and the 1 give me the vertex. Vertex is located at the point 2, 1. Now the axis of symmetry is a line that cuts the parabola in half, so the two halves are mirror images of each other. The axis of symmetry is always going to run through the vertex. The vertex always marks that kind of halfway point, symmetric point of the graph. And so the axis of symmetry, I have it drawn on my picture. It's a vertical line, and it's the line x equal 2. The 2 matches the x value on my vertex. And that's not a coincidence. Axis of symmetry always runs through that vertex. All right, what about the domain and the range? We're dealing with a quadratic function. So the domain is all real numbers. We can plug anything in for x. And we can also see based on the graph, the arrows go to the right forever, to the left forever. So domain is all real numbers, or negative infinity to infinity. Now for the range, for the y values, this function does have a minimum value. That vertex is actually the minimum value. And so this graph starts at y equals 1, and then it goes up forever. So my range is 1 to infinity. Here's another example. Same problem, different function. We've got f of x equals negative 2, x plus 1 squared. We're going to find the vertex, axis of symmetry, domain, range, and graph. So this time, I'll find all these quantities first, and then I'll make my graph. So based on the equation, I know that the vertex has to be negative 1. That plus 1 actually shifts the graph to the left 1. That corresponds with a vertex of negative 1. And then notice there's no plus a number. That means the y value of the vertex is 0. So my vertex is at negative 1, 0. Or in other words, my h is -1, k is 0. Now the axis of symmetry always runs through the vertex. It's always going to be a vertical line, so it's going to be x equal whatever the x value of your vertex is. So in this case, x equal -1. The domain is all real numbers. That's true for all of our quadratic functions. We can plug anything in for x. Now for the range, we're going to have to do a little bit of thinking. And I'm actually going to graph this function to help me do my thinking. So if I think about my graphing transformations, here's my parent function, y equals x squared. This +1 inside the parentheses takes my graph and shifts it to the left 1. And now I can actually visually confirm that I was right about the vertex. It's now located at the point -1, 0. All right, what does this -2 do? The -2 takes all the y values and multiplies them by -2. That's going to stretch the graph vertically and reflect it over the x-axis. So this vertex, the point -1, 0, stays where it is because 0 times -2 is 0. But the point 1, no, it's not 1, that's 0, 1. The point 0, 1, we take the y value, we multiply it by -2. That becomes 0, -2. And same thing with the point -2, 1. That becomes -2, -2. So my graph is a little bit skinnier, it's been vertically stretched, and it's been reflected over the x-axis. The important thing I want to note about this picture is notice that because this x squared coefficient, because this a value is negative, the graph opens down. And that means my vertex is actually my maximum value. So when I find my range is going to be everything from -infinity to this maximum value. So -infinity to 0, including that 0. And again, notice that y equals 0 corresponds with my vertex. So when you're working with quadratic functions, the vertex is always going to be a maximum or a minimum. If the a is positive, the graph opens up, the vertex is a min. If a is negative, the graph opens down, the vertex is a max. All right, what if we aren't given our function in standard vertex form? How can we put something like f of x equal x squared minus 6x plus 2 in vertex form? Well, we're going to use the method of completing the square. So to get started, I'm just going to rewrite this problem, and I'm going to leave a little bit of space after my linear term, after the term with the x. So I've got, just copy down the same function, I just left a little bit of space between the minus 6x and the plus 2. And now I'm going to complete the square. So I look at the minus 6, I look at the number in front of the x, divide it by 2. So minus 6 divided by 2 is minus 3. I square it, I get 9. So to complete the square, I have to add 9. But I can't just add 9 to my function, that changes it. So I'm going to also subtract 9. If I add 9 and I subtract 9, now my function is unchanged. Essentially, I've just added 0. Okay, so I added 9 and then I had to do the opposite. I'm going to subtract 9. Now I can take my first 3 terms and factor those as something squared. I also did 2 minus 9, which is minus 7. The first 3 terms, the x squared minus 6x plus 9, can be factored as x minus 3 squared. I got the minus 3 because that was half of the negative 6. So x minus 3 squared minus 7 is this function in vertex form. Now that the function is in vertex form, we actually know the vertex will be at 3, -7. Although they didn't ask us about that, but might as well write it down for completeness. Based on this, I know my vertex is at 3, -7. My axis of symmetry goes through the vertex, so it's going to be x equal 3. The A value is positive, so it opens up. That means the vertex is a minimum, and my range will be -7 to infinity. And the domain, of course, is all real numbers. All right, let's do a couple more that involve completing the square. So put in standard vertex form. Does the function have a maximum or minimum value? What is that value? Where's the function increasing? Where is it decreasing? All right, so we have a lot of questions to answer, but let's just start with the first thing. Put in standard vertex form. So I'm going to have to use that method of completing the square again. Completing the square, though, really only works when our first term is an x squared. So I rewrote my function, and I just moved the -12 to the end so that there would be some more space. I also looked at my first two terms only, and I factored out the -2, or divided out the -2, because I want the first term to be an x squared. So if I pull a -2 out of -2x squared, I get x squared. If I pull a -2 out of a -10x, I get a positive 5x. Again, when you're factoring, you're dividing that number out. -10 divided by -2 gave me that +5. You can always check to see if you've done this step correctly by distributing the -2 and making sure you get what you started with. But the important idea is we need to have a 1x squared, because now we can use that process of completing the square. We're going to take the number in front of the x, it's a 5, divide it by 2, and square it. 5 divided by 2, can't do much with that, so I'll just square it now. 5 squared is 25, 2 squared is 4. So to complete the square, I have to add 25/4. And I put that inside my parentheses because that goes with my x squared and my 5x. Now I just added a number, so I'm going to have to do the opposite. Subtract whatever I added to keep this function balanced or unchanged. But we have to be really careful. Because I put the 25/4 inside the parentheses, the -2 applies to that. So technically, I have added -2 times 25/4. -2 times 25/4 is -50/4, which can be reduced to -25/2. So technically, we just added -25/2, or subtracted 25/2. So we're going to have to do the opposite, which would be adding 25/2. All right, now let's try to do some simplifying. And again, at this stage, if you're not sure if you're doing this correctly, try distributing, combining like terms, and you should get what you started with. All right, but let's see, we can factor the perfect square trinomial. It's going to be x plus whatever you squared, so 5/2. And then I'm going to take -12 plus 25/2. So I have my work over to the right. I got a common denominator. -12/1 became -24/2. Plus 25/2 is 1/2. So finally, after all that work, there's my function in standard or vertex form. The next question I'm asked is, does this function have a maximum or minimum value? We can answer that by determining whether the graph opens up or opens down. Since my a value, the number in front of the parentheses, is negative, that means the graph opens down. If the graph opens down, the vertex has to be a maximum. So this function has a maximum value, and that maximum value is 1/2, is that y value of the vertex. So based on my equation, my vertex is located at -5/2, 1/2. And so this function has a maximum value of 1/2, and that occurs when x equals -5/2. Again, the -5/2, the 1/2 are my vertex. Graph opens down, so it's a maximum. All right, the next question is, where is the function increasing and where is the function decreasing? The graph is increasing when, if you read from left to right, it's going up. So on the left side of this graph, it's increasing. And to answer this question, you're going to list the x values where it's increasing. This graph is increasing from the left side, which is negative infinity, until you get to that vertex, which is negative 5/2. So it's increasing from negative infinity to negative 5/2. The other half of the graph is decreasing or going down. So that would be from x equal negative 5/2 all the way to x equal infinity. Here's another example. In my next example, we're just given a picture, and we're asked to find the equation of the function shown. So the first thing I would do is look for the vertex, and we can see on this graph that the vertex is located at 2, 7. So in vertex form, my function is going to look like f of x equals a, we don't know what that is yet, x minus 2 squared plus 7. So the first step is to get the vertex, and you can plug that in for your h and your k. Now to get the a value, you can find any other point on the graph. So looking at this graph, I notice a place where the curve goes exactly through the corner of a box. Looks like that's the point 3, 5. So this graph also contains the point 3, 5. I can use that information to solve for a. Specifically, I am going to take the 3, plug that in for x, and plug the 5 in for f of x. So then to solve, let's see, 3 minus 2 is 1, so I've got 5 equals a times 1 squared plus 7. 1 squared is 1, so this simplifies down to 5 equals a plus 7. We subtract the 7, we get a equals negative 2. And so plugging that in, there's my final answer. F of x equals negative 2, x minus 2 squared plus 7. We can also solve applications that involve quadratic functions. Specifically, if a problem is asking for a max or a min, and you can write a quadratic function, that max or min needs to occur at the vertex. So let's take a look at one specific example. This problem says a rectangular dog park is split into 2 pens using a total of 300 feet of fencing. What dimensions will maximize the total area enclosed? So I'm going to draw a picture. So we've got this rectangular region, and then we're going to put a divider in it so it's been split into 2 pens. I'm going to label some things. I'm going to call the width of this pen x, and let's call the total length y. So what we're trying to do here is we're trying to find maximum area. What will maximize the total area? So I'm going to start by writing an equation for area. The area of this rectangle is its length times width, or x times y. So I have an equation for area, it's x times y. But my problem is this equation has 2 variables. It doesn't really look like any of those quadratic functions we've been dealing with. And so our goal is going to be to get this equation in terms of 1 variable only. And it turns out there's a piece of information that we haven't used yet. It says we have a total of 300 feet of fencing. So I'm going to write an equation using that idea. If the total number of fencing equals 300, I have 1, 2, 3 fences of length x, and 1, 2 fences of length y. That means 3x plus 2y is my total fencing and has to equal 300. So now that I have a relationship between x and y, I can take that equation and solve it for y. So I'm going to minus the 3x and then divide everything by 2. And that tells me that y equals 150 minus 3 over 2 times x. Now I can take this expression for y, this 150 minus 3/2 x, and I'm going to plug that in for y in my area equation. So my area equation is now x times 150 minus 3/2 x. Or if I distribute the x, 150x minus 3/2 x squared. And so after all that work, I now have a quadratic function that's in terms of one variable. So I have an equation with an x squared. I don't have any other variables. And this is an equation for area. So if we want to find the maximum of this function, the maximum area, that means we're going to have to find the vertex. The vertex will be our maximum because our a, the number in front of our x squared, is negative. So the graph must open down. The vertex is a max. So I'm going to try to find the vertex of this function. We'll see eventually that there's two ways that we can do this, but I'm going to start by using that method of completing the square to put this in vertex form. So if I'm going to complete the square, the first thing I have to do is factor out the negative 3/2 because I need that x squared to be by itself. So I get a equals negative 3/2 x squared. And then I also have to take the negative 3/2 and divide that out of the 150. So I'm going to take 150 and divide it by negative 3/2. To divide by a fraction, copy dot flip, you multiply by its reciprocal. So 150 times minus 2 is minus 300 over 1 times 3, which is 3. And that simplifies, oh, here it is. That simplifies to negative 100x. So negative 300 divided by 3 is negative 100x. So all I've done at this stage is factored out the negative 3/2 or divided that negative 3/2 out. Now my next step is to complete the square. So I take the negative 100, number in front of the x, divide it by 2. That gives me negative 50, and then I square it. 50 squared is 2,500. So I'm going to be adding 2,500 inside the parentheses. Now because the 2,500 is inside the parentheses, we've actually added negative 3/2 times 2,500. Negative 3/2 times 2,500 over 1. Let's see, I decided to reduce before multiplying because I know 2,500 divided by 2 is 1,250. And then 1,250 times minus 3 is negative 3,750. So technically I have added negative 3,750, or I guess subtracted 3,750. So to do the opposite, I have to add 3,750 outside of the parentheses. Now we can factor our perfect square. This trinomial turns into x minus 50 squared. And there's our function in vertex form. Based on the function in vertex form, I know that the vertex is located at 50, 3,750. All right, back to this problem and the questions that they're asking. They're asking us to find the dimensions of our pen. And so the dimensions would be x and y. X in the function is called x, and I computed the x value of the vertex to be at 50. So the width of this pen has to be 50 feet. Now y is what I call the length of my rectangle. The y value of this function is actually an area. I don't want the area, I just want this y value. So I can get that y value using the fact that earlier I had the equation 3x plus 2y equals 300. That was my perimeter equation. So I can take the 50, x equals 50, plug that in. I get 3 times 50 plus 2y equals 300. Subtract 150 from both sides, so 2y equals 150. Divide by 2, y equals 75. So the dimension should be 50 feet by 75 feet. That will maximize the total area enclosed if you have 300 feet of fencing. Now this problem was an application problem. There's a lot going on here. We had to write an equation of a function that gave us area, and then we had to find the vertex of that function. So I went through and used my method of completing the square to find that vertex. But it turns out we can come up with a pattern or a formula for the vertex. And I want to show you where that comes from. If you start with the most general quadratic function, f of x equals ax squared plus bx plus c, you can take this formula or this general function and complete the square to put it in vertex form. So let's do that and see what happens. If I want to put this in vertex form, my first step is to factor the a out of the first two terms. Factoring the a is the same as dividing the a out. So once I factor that a out, I have an x squared plus b over a x. To complete the square, I take the number in front of the x, b over a, divide it by 2, and square it. B over a divided by 2 is b over 2a, and if I square that, I get b squared over 4 times a squared. So I'm going to take that b squared minus 4 over a squared and add that into my parentheses. Okay, what do I have to subtract? Well, technically, because that b over 4a squared is inside the parentheses, technically that a applies to it. So if I take a times b over 4a squared, that simplifies down to b over 4a. The a's cancel out. So technically I have added b over 4a, and so that's what I'm going to subtract. Now we can factor, and this turns into a times x plus b over 2a squared plus c minus b over 4a. So this function is now in standard or vertex form. And based on this, I know the vertex has to be located at negative b over 2a. Based on that information, I can go back to my problem, and I can use my formula, negative b over 2a, to find the x value of my vertex. So back to my original problem, the problem we started with. Here's the area function we found for our rectangles. A equals negative 3/2 x squared plus 150x. So using the formula I just found, the x value of the vertex is negative b over 2a. We can let a equal the number in front of the x squared. So a is negative 3/2, and b is the number in front of the x, 150. I'm going to plug that into my formula, negative b, so negative 150 over 2 times a, 2 times negative 3/2. The denominator simplifies down to negative 3, so negative 150 divided by negative 3 is 50, and that's going to be the x value of my vertex. That's actually what we got before. 50 feet would be the width of this rectangular pen. We would still have to find that y value using the same method I did before by taking our 50 and plugging it into our perimeter equation, but at least this formula gives us a slightly faster way to get that x value of the vertex. So again, our vertex formula is negative b over 2a. Alright, that was my last example. I know there's a lot going on in this video, so please let me know if anything is unclear.